We have mentioned several times the need for storage if we want to be successful with having renewable energy sources like solar and wind with their intermittencies to be part of the real energy solution. So we will have two podcasts, one on energy storage at utility scale, which is stationary, and the other one is distributed, where you have some ideas of moving energy storage, but also mostly at the microgrid scale or nanogrid scale that we talked about before. Okay, the capacity is going to be vastly different as well. The ranking by 2050 here is number 77. It's an enabling technology again. Cost and savings are embedded in renewable energy. This is like the grid flexibility that we talked about before. So we don't talk about carbon savings and so on to avoid the double counting, which is already included in the renewable energy sources. So here is an example with the solar wind power together being produced and the energy storage sitting right there next to it. The technologies that are already online at various scales include batteries, range of electrochemical storage solutions, including advanced chemistry batteries, flow batteries, and capacitors. So flow batteries, there is a difference between the way the exchange works between positive and negative electrodes and so on, that I won't get into, but you can look it up. Thermal, capturing heat and cold to create energy on demand or offset energy needs. We talked about this already a little bit, where you heat or melt things like salts, molten salts, to store energy and extract it when there is a demand. And wind and solar cannot be turned on whenever you want. In fact, they cannot also be turned off easily. Well, they can be, but when there is energy being produced, it's better to find ways to use that excess energy when they are fully operational, to store them in other ways, which include things like mechanical storage, where you lift up water like pumped hydropower, or you move a train up the hill and then let it roll down, and there is some regenerative braking system which can produce energy from the flow down, the gravity, when needed. Mechanical storage also includes other innovative technologies to harness kinetic or gravitational energy to store electricity. So that's what you do when there is excess energy, like early in the morning or late at night. You can store those energies when the demands are low. Peaker plants or peak power plants have typically been used to crank up dispatchability or energy to meet demand, but those are typically high emission power plants, so storage is going to make them hopefully completely redundant. Hydrogen, another storage, is excess electricity generation to be converted into hydrogen via electrolysis and stored. So producing hydrogen for fuel cells or for other forms of energy use, energy generation, requires electrolysis and so on. So if there is excess electricity, that can be used to generate hydrogen in off-peak hours, to store it then for later use. Pumped hydropower, creating large-scale reservoirs of energy with water. So you go from one lower storage tank to an upper one when there is excess power, and then when you need it, you just actually drive a hydro power plant with that energy flowing down the hill by gravity. Sounds straightforward, right? So here are some of the characteristics of selected energy storage systems from the World Energy Council. So you have pumped hydro, compressed air, molten salt, we talked about, thermal storage, lithium-ion batteries, which are very common now, lead-acid batteries, the older ones, flow batteries that I just mentioned, hydrogen, and flywheels. So you can use flywheels to store energy as well. Here are the maximum power ratings from the highest pumped hydro down to the lowest in flywheels. Discharge times 4 to 16 hours. So there is a crank up time that we talked about when we talked about grid flexibilities. Remember? So compressed air can be 2 hours to 30 hours. Molten salt can be pretty fast, just a few hours. Lithium ion batteries obviously can be very fast, 1 minute to 8 hours. Lead acid batteries similar, flow battery, hydrogen, and so on. Maximum life cycles over time again varies depending on the technology, and you can see that some of them have a very, very long lifetime in terms of maximum cycles you can crank through them. Okay, energy density is down here. So even though this is maximum power rating is very high, energy density can be very low in terms of how many gallons of waters you have to lift and flow down to create megawatts of energy. But efficiency is very high, but efficiency is also very high for lithium ion. Why am I having trouble with lithium ion batteries? Molten salt also has high efficiency, and flywheel has high efficiency, but power rating is very low. So there are all kinds of compromises. This is just an example from the book chapter, which is showing these plus and minus signs indicating the poles on the new energy storage facility at Fraunhofer Institute in Germany, Magdeburg. During a full-scale test, the entire Fraunhofer Research Center was supplied with energy from the battery. The lithium-based storage system has an average capacity of 0.5 megawatts per hour and an output of 1 megawatt. So it depends on how long you run it. The storage battery is housed in a 26-ton transportable container. So this is a storage that is transportable. This type of equipment is designed to stabilize intermittent and variable energy. Again, a enabling technology to deal with renewables with intermittency issues. This is from Irina again. Benefits are listed for batteries as providing services for systems operation and for solar PV and wind generators. Defer investments in peak generation and grid reinforcement. So the highly polluting peaker plants and grid reinforcements can be made redundant with this. So you have renewable generators, batteries, transmission networks, again batteries, distribution networks, batteries, and then end users down here. So renewable generators include reduced renewable curtailment as a benefit, renewable capacity firming. System operation is benefiting in terms of frequency regulation, flexible ramping up and down, black start services, investment deferral. So transmission and distribution congestion relief can be accomplished. Energy shifting and capacity investment deferral can also be accomplished with these storage systems. Key enabling factors include reduced upfront costs conducive to regulatory frameworks, pilot projects, and why does this happen, and knowledge dissemination. Okay. 3 is a snapshot. There are in terms of capacities around the world. In 2017, there was 10 gigawatts of battery storage deployed globally. Batteries with a total annual production of 27 megawatt hours are providing a quarter of the total enhanced frequency regulation capacity in the UK. Demonstration project in the US showed that a 4 megawatt 40 megawatt hour battery can save $2 million US in fuel costs and 400 hours of grid congestion. Of course, there is also the co-benefits of reducing emissions, right? So this is the increasing share of lithium ion in annual battery storage capacity additions globally, going from 2011 to 2016 with lithium ion flow batteries, supercapacitors, lead acid, sodium sulfur batteries, zinc air, flywheels, compressed air, and so on. So you can see that the capacities have gone from This is the share of capacity additions by technology for each of those. And here is the capacity addition in terms of gigawatts, going from 0.25 to now 1.62. So that's a good trend, I would say. Here is stationary battery storage capacity growth from 2017 projected to 2030 in terms of gigawatt hours, photovoltaics, behind the meter, and so on, again from IRENA. Here is the reference case for 2017. This is the low scenario and this is the high scenarios, and you can see that the 2030 scenario here for BTM batteries with rooftop PV is so behind the meter battery together with the utility scale batteries and a BDM battery with rooftop PV retrofit is supposed to double compared to the 2017 reference scenario. In the low case, it's just about I don't know, close to 200 gigawatts, gigawatt hours. Okay. This is just services offered by utility scale battery storage systems. So system operations, investment deferrals, solar PV and wind generators, and mini grids that we talked about. They allow for frequency regulation, flexible ramping, black start services, energy shifting and capacity investment deferral, transmission and distribution congestion relief, reduced renewable energy curtailment, capacity firming, reduced reliance on diesel generators, which is really not a very environmentally friendly way to generate energy on call, right? So, taken on its own, the impact says the production of energy storage does not reduce emissions, it's just an enabler. So energy storage enables adoption of wind and solar energy, makes it easier to make them part of the grid. No carbon impact numbers are included above in order to prevent double counting with variable renewable energy solutions themselves. As with the other forms of grid flexibility, the costs and total growth are not modeled directly, but they are treated as part of the overall renewable energy grid or portfolio. Okay, let's leave it there.